Hello friends, I welcome you in lecture number 28 on logic. In this lecture we are going to discuss about quantifiers. We have taken an introduction of predicates in previous two lectures. Now we are familiar with predicates as well as statement functions. We know that predicate is nothing but an expression which describes the property of some objects, or it is a common feature. And we are familiar with statement function also. Statement function is denoted by this capital letter for predicate, and in the bracket we write the corresponding variable. So if I am writing capital P of x, then P is the predicate and x is the variable. And we know that statement function is not a statement, but by taking particular values of variable in statement function we obtain different statements. So this is another way of obtaining or writing statements using statement functions. Now we can find out statements by considering quantification of statement function also, that we are going to discuss in this lecture. So first we consider particular statement function. Suppose I consider that P of x denote the statement function that x is positive, that we can write as x is greater than 0. And we know that this statement function will become a statement if we take particular values of x. Suppose I consider x equal to 2, then I will obtain the statement 2 is positive. That means 2 greater than 0 is a particular statement which is having truth value t. If I consider P of minus 1, then I will obtain minus 1 is greater than 0, which has truth value f. So by considering particular values of variable in the statement function we obtain different statements. Now sometimes this statement function might be true for all values of x in a particular domain or in a particular set. For example, if I consider set of natural numbers, then we can say that if x is natural number, that is for every x in the set of natural numbers we know that x is always positive. So if I consider domain as the set of natural number, then I can say that this statement function is always having truth value true. So if we quantify the statement function, then we will obtain statement function. If I am writing Px x greater than 0, then this is not a statement, it is a statement function. But if I am writing that for every x in the set of natural numbers x is greater than 0, then this is a statement which is true for every natural number. So this process is called quantification of statement function, and we are using this upside down a, and this upside down a symbol is nothing but quantifier, and it is known as universal quantifier. Universal quantifier means we are using this type of things for all x in the given domain or for every x in the given domain. So this statement function can be quantified in this way. We can write that for every x Px is true, that we can write simply in this way. First we denote Px by x is greater than 0, and when we write for every x Px, that means every natural number is greater than 0. So this is called quantification of this statement function. This symbol is called universal quantifier, and it means for every x or for all x. But here domain is important another name for domain in the language of logic is universe of discourse. We will remember this word for the domain. Universe of discourse is another name for domain. So whenever we are using this type of quantification, universe of discourse is important. If it is not given, then we should assume some domain or some universe of discourse such that that statement function is true for all values of x in that domain or for some values of x in that domain. So whenever we want to write or this type of statements in symbolic form, for example, here I can write that every natural number is positive. Okay, we have written this statement in symbolic form. Every natural number is positive. So what I am doing, first I assume that suppose px denote that x is greater than 0, and here we are given every natural number. That means the universe of discourse or domain is the set of natural numbers. So I can write in this way: for all x, p of x, or I can write for every x in the set of natural numbers, px is true. Px is x is greater than 0. Some authors are writing in this way also. They are writing for every x in the bracket and this also in the bracket. So some authors are using brackets, some authors are not using bracket. They write simply in this way. Some authors are simply using x instead of this symbol. For every x, px is true. So we should be familiar with different notations. So this is about universal quantification of statement function, given statement function. So that I have written here. We are going to discuss about two types of quantifications. One is universal quantification, and this symbol is called universal quantifier. Another is existential quantification, and this symbol is called existential quantifier. We will talk about existential quantification in next lecture. So here I have written all these things. When all the variables in a statement function are assigned values, we get a statement or a proposition with a certain truth value. That means if we have statement function, then by taking particular values of variable, we obtain different statements which are having truth values. However, there is another important way called quantification to create a statement from a statement function. So we can use another way as we discussed here. For every x, x is greater than 0. So this is called quantification of the statement function px, which is x is greater than 0. So this is another important way to create a statement from a statement function. Whenever I am writing that for every x, px, where px denote x is greater than 0. So whenever I am writing this, then this is not statement function now. It is a statement, because if we consider universe of discourse or domain as the set of natural numbers, then this is always having truth value capital T. It is always true for every x in the set of natural numbers. So this becomes statement when we quantify this statement function. This is statement function because here x is greater than 0. X can take any value. We have not specified any domain here. Suppose we are using x equal to -2, then it is going to be negative. But if we specify the domain and if we use this universal quantifier, then we obtain this statement which is always true. So that is another way to create a statement from a statement function, and that way is called quantification. So we are going to discuss two types of quantification. One is universal quantification, another is existential quantification. Now, as I discussed, many mathematical statements assert that some property is true for all values of a variable in a particular domain. That domain is also called universe of discourse or domain. Such a statement is expressed using a universal quantification. The universal quantification of a statement function px is the statement that asserts that px is true for all values of x. This is very important. Universal quantification asserts that statement function is true for all values of x in the universe of discourse, and the universe of discourse, that is domain, specifies the possible values of the variable x. For example, if I consider that px is x square is greater than 0, then if I consider universe of discourse or domain as the set of real numbers, then we know that if we take any real number, its square is always greater than 0, and if we include 0, then it is non-negative. So if I consider px as x square is non-negative, then this is always true for all values of x in this domain. So that I can quantify as for all x px. This means for every real number x, x square is always non-negative, or we can say that px is true for all values of x in the set of real numbers. So if they ask you to write down the definition of universal quantifier, you can write in this way: the universal quantification of propositional function, another name is statement function, denoted by px, is the proposition or statement. We know that proposition or statement is a declarative sentence that is either true or false. So the universal quantification of statement function px is the statement px is true for all values of x in the universe of discourse. Whenever I write that for every x p of x, that means statement function px is true for all values of x in the universe of discourse, and this notation for all x px denotes the universal quantification of statement function px, and this symbol is called universal quantifier. And if we write this statement for all x px, then this we read as for all x px or for every x px. Now we consider certain examples and we see how we can create the statements from statement function and how we can decide their truth values. So in first example, px denote the statement that x plus 1 is greater than x. So this is statement function px is x plus 1 is greater than x. What is the truth value of the quantification for all x px, where the universe of discourse consists of all real numbers? So here universe of discourse or domain is the set of all real numbers, and we have to determine the truth value of this quantification for all x px. That means we have to check whether for every x this is true or not. X plus 1 is greater than x. Now if x is any real number, then x plus 1 is greater than x. If 1 is greater than x minus x, that is 0. and this is true if 1 is greater than 0. So if I take any real number, x plus 1 is greater than x is true if 1 is greater than 0, and we know that this is always true. Therefore x plus 1 greater than x is true for all real numbers or for every x in the domain of discourse. Therefore truth value of this quantification for all x px is true. So we can write that clearly: x plus 1 is greater than x for every x in the set of real numbers. Therefore for all x px has truth value capital T, or we can write that it has truth value true. It is always true for every x in the set of real numbers. I have taken another statement function which is denoted by qx. Qx denote the statement function x is less than 2, and here the universe of discourse is again set of all real numbers, and we have to find the truth value of the quantification for all x qx. That means we have to check whether for every x in the set of real number x is less than 2. So this is obviously not correct for every x in the set of real numbers. Suppose I consider x equal to 3, then I will obtain 3 is less than 2, which is not true. Therefore truth value of this quantification is f, or it is false. So for all x qx has truth value capital F. So whenever we want to check the truth value of the universal quantification, then truth value is true if that statement function is true for all values of x in the given domain or in the universe of discourse, and truth value is false if there exists at least one x in the domain such for which given statement function is not true or is false. So here statement function is x is less than 2, domain is the set of real numbers, and we find 3 in the domain such that qx is not true or qx is false. Therefore truth value of this quantification is false. I have taken another example. What is the truth value of for all x? Statement function is x square greater than or equal to x if the universe of discourse consists of all real numbers. And what is the truth value if the universe of discourse consists of all integers? So here we have to find the truth value for different domains for this same statement function. Statement function is x square is greater than or equal to x, that we can denote by capital P of x, and domains are, first we have to check the truth value for x in the domain set of real numbers, and then we have to check for set of integers. So before that, first we check that for which values of x this is going to be correct. X square is greater than or equal to x if x square minus x is greater than or equal to 0. This we can rewrite by taking x common. We have x times x minus 1 is greater than or equal to 0. So this is going to be 0 if x equal to 0 or x equal to 1. Now suppose we have this real line. Here I have 0, here I have 1. Now suppose my x is here, that is x is greater than 0 if x is to the right side of 1, and x minus 1 is also greater than 0. So this is true, or I can write that x into x minus 1 is greater than or equal to 0 if x is greater than or equal to 1. For x equal to 1, I will have 0 value. If x is greater than 1, then x minus 1 is positive, x is positive, therefore this is going to be positive. Now suppose x is less than or equal to 0, then we can see that if x is less than 0, then x is less than 1 also, therefore x minus 1 is negative. So if my x is on this side less than 0, then this is going to be negative and this is also negative. So negative, negative, positive. So if x is less than or equal to 0, then this is going to be non-negative. For x equal to 0, it will be 0, and for x less than 0, it is going to be positive, because if x is less than 0, then x is negative. If x is less than 0, that means x is less than 1, therefore x minus 1 is also negative, and product of two negative numbers is positive. So now x square is greater than or equal to x. This is true if x is greater than or equal to 1 or x is less than or equal to 0. Now suppose x is somewhere in between 0 and 1. Suppose we consider x equal to 1 by 2. Then we can see x into x minus 1. X is 1 by 2. So I put x equal to 1 by 2 here. So I will have 1 by 2 into minus 1 by 2, which is negative. So whenever x lies between 0 and 1, in that case x is going to be positive if x is somewhere here, but x is going to be less than 1. So whenever we have 0 less than x less than 1, that means x is greater than 0, but x is less than 1, therefore x minus 1 is going to be negative. So positive into negative, that is going to be negative. So if x lies between 0 and 1, then this is having truth value false. This is going to be negative if x lies between 0 and 1. Now suppose our domain is the set of real numbers, then we can say that for x equal to 1 by 2, this is not true, therefore this quantification is having truth value false if domain is set of real numbers. But suppose domain is the set of integers, then now we know that if x lies between 0 and 1 only, this is false. If x is in between 0 and 1, then this is going to be false. But if we consider x in this set of integers, then there is no integer between 0 and 1, therefore this is going to be correct if x is integer. If the domain is this set of integers, then this is always true, because this is true if x is greater than or equal to 1, that is 1, 2, 3 and so on, or if x is less than or equal to 0, that is 0, minus 1, minus 2, etc. So if we consider x in the domain which is set of integers, then there is no integer in between 0 and 1, and this is not true for x in this interval. Otherwise it is true everywhere. So whenever x is in the set of integers, this is going to be correct. Therefore if we consider universe of discourse as the set of integers, then this has truth value true. And if we consider domain as set of real numbers, then this has truth value false, because it is not true for x equal to 1 by 2. So these things we have to write systematically. Here I have written. that x square is greater than or equal to x if and only if, this is short form for if and only if and only if x square minus x is greater than or equal to 0, if and only if x times x minus 1 is greater than or equal to 0, and if and only if x is less than or equal to 0 or x is greater than or equal to 1. That means if x lies between 0 and 1, then this is false. And for example, for x equal to 1 by 2, which is in between 0 and 1, we can see that x square is 1 by 4 and x is 1 by 2. So here we cannot write that x square is greater than or equal to x for x equal to 1 by 2. Therefore, this quantification for every x such that x square is greater than or equal to x is false if the universe of discourse consists of all real numbers. And since there are no integers x with 0 less than x less than 1, this quantification is true if the universe of discourse consists of all integers. So in this way you can determine the truth values of given quantification of given statement function, and you can see that it may be different for different domains. And this is another example. What is the truth value of quantification for all x px, where px is the statement x square is less than 10 and the universe of discourse consists of the positive integers not exceeding 4. So here universe of discourse or domain is the positive integers not exceeding 4, that is we have to consider 1, 2, 3 and 4, we cannot consider 5. So this is the domain for this quantification, and the statement function is x square is less than 10, and we have to check whether for every x px is true or not. So we can check by taking particular values of x. If I take x equal to 1, 1 square is 1, which is less than 10. If I take x equal to 2, I will have 4, which is less than 10. For x equal to 3, I will have 3 square, which is 9, is less than 10. But if I take x equal to 4, I have 4 square equal to 16, which is not less than 10. So this is not true for all values of x in the domain. If we consider p of 4, then we have 16 less than 10, and it is not true, it is false. And if you see, you can see this is nothing but p of 1 for x equal to 1, this is p of 2 for x equal to 2, this is p of 3, and this is p of 4. So this is going to be correct if it is true for all values of x, or we can say that if all these statements are true, then only this is true. So we can write down in this way also. We can join all these by conjunction operator, p of 1 and p of 2 and p of 3 and p of 4. So if all of these are true, then only this quantification has truth value true, and if at least one is false, then this quantification has truth value false. So here p of 4 is not true, therefore this has truth value false. So we can write in this way also. Here px is x square is less than 10. The universe of discourse or domain is set having 4 natural numbers, and the statement for every x px is the same as the conjunction p of 1 and p of 2 and p of 3 and p of 4. Now what is p of 4? It is 4 square less than 10, and it is not true, it is false, because 16 is not less than 10, and this is nothing but conjunction of these 4 statements, and we know that whenever we have conjunction operator, then result is true if all the statements in the conjunction are true, or if at least one statement in the conjunction is false, then given conjunction is false. So here P of 4 is false, therefore for every x, Px is having truth value false or F. So in this way we can have quantification of statement function denoted by Px, and we will write in this way: for every x Px. Some authors are using brackets also, for every x P of x. So these are different notations and all the notations are valid, and this quantification has truth value true if this is true for every x, if Px is true for every x in the given domain. So this is all about this session. In the next session we will discuss about existential quantifier. Thanks for watching.